Okay, so we're going to be learning about free body diagrams, which are a really important tool that's used in forces problems, just to start analyzing what's going on and eventually to figure out what kind of acceleration our system will have. So when you're drawing a free body diagram, there's a couple of guidelines you need to always follow. The first one is whatever the object is, and we usually represent it with a box or a dot, you always have to start your force vectors on the box or on the dot and then go in the direction of the force. So I'll show you guys the right way to do it. And I guess maybe I'll show you guys like a wrong way, just so you know the difference. And then you need to make sure that you label all of your forces. And right now we're going to be very, very careful with our labeling. We're going to say what type it is, whether it's a contact force or a field force. We're going to say what the force is acting on and where the force is coming from, like it's by earth or by a rope or something like that. And then finally, and this last one's definitely more of a guideline. The other ones are closer to being rules. But when possible, we're going to try and draw arrows with appropriate relative magnitudes. So if it should be a big force, we should draw a big arrow. If we know it's kind of a small force relative to the others, we would draw a small arrow. And then if the object's not supposed to be moving, we kind of want to try and have all of the arrows kind of add up to 0. But we'll do that as we go through here. So for this first one, I have 3 examples. First one, I have this car that's going down, not going down a hill, sorry. It's being pulled up the hill by a rope. This is really the same one that we did for our force identification. And in fact, I'm going to draw that circle around my object again. Circle. I'm going to draw it again. And then I'm going to highlight every point where there's contact. That's a great way for us to make sure that when we draw our free body diagram, we get all of the forces. So you can see that there's this contact here along the surface and another contact where the rope is in contact with the car. So from there, we can draw all of our vectors. We have since there is a surface here, we need to draw a normal force. Remember that normal force is always at a right angle to our surface. So this is our Fn, normal force. It's a contact force, and it's acting on the car by the surface. Another force that we have acting on it is we have tension. I'm going to use capital T to represent tension. And then tension is another contact force. It's acting on the car, and it's by the rope. Let's see, next force that we have acting on our system, we have the frictional force, because surfaces can always do 2 forces potentially. They're going to have a normal force, which is at a right angle, and then a frictional force that opposes the motion. So I'm going to draw it about like that. And I'm going to use curvy F to represent that one. Again, this is a contact force. It's acting on the car, and it's by the surface. If at any time, and you guys are going to get super annoyed by this, but we're doing it anyways because it's good for us. Notice that I had on car for every single one of these. Well, that's good because then I was doing the right forces. What you don't want to do is you don't want to add a force like this that says the force normal, it's a contact force on the ground. That would be incorrect because the system that we care about, the object, is this car, not the ground. So we only need forces acting on the car. Still one more force to go though. I've accounted for all of the contact forces, all of the possible things that could be explained by these red points I've done. And then there's one more force, the field force of the force of gravity. So I'm going to do mg here because I just always write it as mg. And then this is the field force. It's acting on the car, and it's by Earth. Okay, So there's the free body diagram for this car. You can see that I have all of my force vectors. I've drawn them all starting at my dot, going the right direction. I've labeled them with what type of force they are, contact versus field. I've verified that they're all acting on the car and not the car acting on something else. And I know who's doing them. These two that are from the surface, so I can check off those. I'm done with those. This one by the rope, so I can check off that one. And then finally the ground, the field force from outside our bubble, because the Earth just kind of acts on everything. Okay, so for our next one, I'm going to do this apple. And I'll do it a little bit faster, I hope. We're just doing the apple that's sitting up there. And it has only two forces on it. It's going to have these vectors here. I wanted to show you guys what I don't want you to do. I don't want you guys to do this. That is not how gravity should act. That is the right direction for gravity, but we want to start at our object and then go in the direction the force is acting. So do gravity down here, not gravity pushing down from that direction. Or we don't want to have like, oh, the book's pushing up this way on the apple. It is, but we represent it by drawing it on the object extending in the direction of the force. So labeling these real fast, this should be once again the force of gravity. It's a field force on the apple by the Earth. And then we have, we'll call this one, yeah, this is just normal force. It's a contact force on the apple by the book. Notice that the table didn't show up anywhere. The table doesn't apply any forces to the apple because the apple isn't in contact with the table. The apple is only in contact right here along the bottom with the book. So that's the only one that we get there. And so if we're checking this off, we have the force of the normal force, and we have the force of gravity outside that. Notice that there is no friction. Friction only shows up when motion is happening or motion could happen. This apple, even if it was on a frictionless surface, would stay put. It's not going to slide a direction. If I started inclining it like that car is, well, then we start having friction. But the apple's good where it is. It's not going to go anywhere, so we don't need friction. All right, last one is this stoplight, and we're going to have. Oh, let's identify it. Look, we have a force there and a force there. So I need to represent each one of those. Oops, make those blue, just so that it looks pretty when I'm done. Notice that, okay, that wasn't perfect, but notice that my force vectors are pretty much right there, the same angle as those tensions, and each one of these is a tension. So we'll call this one T1 and T2. And there's a force of gravity acting downwards on it. And yeah, each tension is parallel to the direction of the wire, and it's pulling up in those directions. So T2 would be a contact force on the light by the rope. We'll call that rope 2. This will be contact on the light by rope 1, sorry. And then this should be familiar by now. Our field force of gravity acting on the light by Earth. So that's how you do free body diagrams. It's a skill that we're definitely going to be doing a lot of practicing. But in case you ever need to look back and see if you're doing it right, these are three examples and kind of just the demo guidelines. So thanks for watching, and I'll see you later.